Microelectronica, this episode is especially useful. In short, space itself is comprised of fundamental quantum fields, one for each elementary particle. Those fields oscillate, vibrate with different energies, and those oscillations are the electrons, quarks, neutrinos, photons, gluons, etc. that comprise the stuff of our universe. Now, these fields are quantum fields, which means their oscillations can't just have any old energy. They can only be excited in quantized chunks, integer multiples of some baseline energy. In each quantum state, so each combination of particle properties, there's a ladder of energy levels, a bit like electron orbitals in an atom. Each new rung of the ladder represents the existence of one additional particle in that quantum state. In fact, the math of quantum field theory is all about going up and down this particle ladder using so-called creation and annihilation operators. We'll come back to those when we talk about Hawking radiation in the future. The bottom of this energy ladder corresponds to these quantum oscillators having no energy, which means there are no particles in the given quantum state. We call this the vacuum state of the field. Inside a perfect vacuum, all of the fields at all locations should be in the vacuum state, exactly zero energy at all times. But here we run up against that pesky Heisenberg uncertainty principle once again. We saw that it's impossible to simultaneously fix position and momentum. Well, it's also impossible to simultaneously perfectly define time and energy. The more tightly we try to define the time window for the behavior of a quantum oscillator, the less certain we can be of its energy state in that time window. On extremely short timescales, a quantum field exists as a blur of